that was our mechanism. We ended at two possible products. We didn't look at an energy diagram, right? Okay, so let's take a look at this energy diagram. Where do you want to start? Reactants, products, intermediates. Reactants is generally a good place to start. We'll go ahead and kind of color code these things. Okay? Both the reactants or both of these products are going to be produced from the same reactant. So we'll go ahead and color that as purple. Because we don't know where anything else is, we'll go ahead and code that roughly halfway in energy. Okay? We're not quantifying, we're approximating these things. Okay? Let's take a look at our products. We'll call this our red product, and we'll call the other one our blue product. Okay? What makes those products reactive? The pi bond. Okay, so which of them has a more stable pi bond? The red one, which means it is lower in energy. Okay? So based off the picture we've got so far, which product would you expect to be your major product?
The red.
The red one. It's the lowest energy. Okay, virtually everything we do drives towards low energy. Okay. The reason why I kind of skipped over the intermediate areas because we got some gray areas floating through there. Okay. So first and foremost, what we're going to do is choose to ignore the presence of the acid. All I care about is the energy of the organic material. So we start with 2 pi bonds, and in our intermediate, how many pi bonds do we have? 1, which would suggest what happens to the energy. Goes down, becomes more stable. However, what else is added in that structure? We have a formal charge. Formal charge is going to be the most reactive thing for us. So where would we expect to place our intermediate? Higher in energy than our reactant. Okay? Which one do you want to place first, red or blue? Blue. Okay, so let's go ahead and place it. It's higher in energy than our reactant, so we'll just kind of arbitrarily place that somewhere like that. So now the question is, where do we place red?
Above it.
Why do you place red above it?
It has a less stable carbon.
If we evaluate the most reactive thing present, the charge, the red one has a primary resonance carbocation. The blue one has a secondary resonance carbocation. Secondary carbocations are more stable than primary. That would put the red one higher in energy. Yeah? Now what happens when we connect all the dots? The thing that's interesting is we get a crossover between those two energy diagrams. Which product would you expect to form first? Why the blue one? It has a lower activation barrier, which means the blue one should form fastest, which is kind of counter to what we talked about, because didn't we say the red one was most stable? So which product do we get? Do we get the fast one or the stable one? That all depends on the conditions of our reaction. Okay? Those conditions really hinge on the energy necessary to clear our activation barriers. Okay? If we heat this reaction up, we've got enough energy that we can clear the activation barrier for the red one. Once I form red product, because it is so stable, I cannot reverse that reaction. If I form the blue product and I'm at high energies, do I have enough energy to reverse the reaction? Yes. The instant it reverses, we now have this complex equilibrium. That reversible reaction is going to come up with a balance. The red one's going to come up with a balance too, except you can't reverse it. So given enough time and energy, all of our product becomes the red one. If we cut the time down and now say do it very fast, okay, and we reduce the temperature, what happens to our product? We get the blue one. So if we change the temperature and time conditions, we can change which product we get. Okay? Instead of referring to these as the fastest and stablest, we refer to them more appropriately as the thermodynamic product and the kinetic product. What you did in 152 was study kinetics and thermodynamics. All of 152 was kinetics and thermodynamics. You just quantified the hell out of it. We're not going to quantify it. We're going to look at rough energy diagrams and predictions behind those to decide which products we should get, be it kinetic or thermodynamic. That takes a little bit of practice to deal with. We can't use the numbers to allow it to solve. Okay? We could theoretically bring in the numbers, but then all you're doing is retaking 152. Okay? So what OChem2 is layering on is our approximation abilities. Can we use structures and our rough approximations of energies to predict these reactions? And that's kind of cool, because what ends up happening? Organic chemists can predict with roughly 95% accuracy their reactions. General chemists are better because they can go through and predict and they get 99%. Fantastic. Either way you calculate it, you're still an A. Okay? Except the general chemist has to do a whole bunch of calculations in mathematics that only work for that one reaction. The organic chemist can kind of hand wave their way through it, and they can apply that to multiple reactions. So we can pick up a lot more speed behind our predicting abilities. Kinetics and thermodynamics is a challenging concept to deal with. We'll see it happen in a lot of places. This is the first place it really appears as far as our course is concerned. The next place, those people in the lab should know, Diels-Alder is a kinetic and thermodynamic argument as well. Okay? So kinetic and thermodynamics shows up in a lot of different places. You're expected to watch a play-pause-it video about kinetics and thermodynamics. Okay? I think I talked through 4 different reactions. Those 4 different reactions we will see throughout the semester. Okay? So some of them are more complicated because we haven't gotten there yet. Some of them are a little bit simpler. This is the simplest version of it. Kinda? Okay. You should review that video. In fact, I think you get points for it. Which, by the way, play-pause-it is now available again. Okay. Chapter 25, radical chemistry. This is really just here as kind of a quick overview. Radicals don't react well on their own. Alkanes don't react well on their own. We need something to get them to react. That's where our radical chemistry comes into play. Okay. Radicals are there to really get things to react that we wouldn't expect to react. And that's because radicals are highly unstable. We have an unpaired electron. Those unpaired electrons aren't good. They seek out a pairing somehow to neutralize that free radical state. So if you've heard of free radicals or bad free radicals in your body, okay, free radicals are why we live. Okay? Oxygen, okay? Pure respiration is a free radical reaction. Okay? We have to have free radicals to live. The question is, where are those free radicals? Okay? To live, would you make the argument that we need gasoline?
No.
Okay? What powers your house at night?
I don't need that.
Okay. To live in our current existence, do we need gasoline? Yeah. To even live in Africa, do you need wood? Do you need fire?
Yeah.
Okay. We could adjust and completely remove fire as a part of this, but we still need that energy source. Okay. So if we just boil it down to just say fire instead of gasoline, do we need fire to exist? Yes. What if you are set on fire? You don't exist. So fire is a critical aspect for our existence, but where it happens is very important. Same thing with our radical chemistry. Oxygen is a very important free radical reaction that we need to exist. but we have to control where it happens in our body. Because if it happens everywhere, we die very fast. Okay? And so that's why our bodies have built systems to scavenge free radicals. Okay? So they react with them and create neutral species. Okay? What would cause an electron to become more stable? Having a buddy, pairing it up. What else? You're stuck with a radical. So if we paired it up, we now jump to charge. What else could you do to stabilize if not looking at charge? Size. Okay. The bigger the atom holding the radical, the more stable it is. Okay. This is one of the reasons why oxygen radicals are dangerous. They're very small, so they're very reactive. Bromide radicals, much larger, less reactive. Okay. What else could we do to stabilize it? I won't accept that yet. Electronegativity. Notice in our lists of radicals here, okay, we don't see hydrogen. Okay, we don't see our metals, typically. Why not? Those are so reactive that they're harder to control. Okay? After that, we can deal with resonance. This first one can do radical stabilization. Okay, so we're still using the exact same principles that we've been using for all stability to explain stability of radicals. Okay? When thinking about radicals, these are all examples. These tend to be giant red flags that you're doing a radical reaction. Okay? Particular reagents. Remember, radicals are not easy to make, so I have to get them from somewhere. That's a very common place to get the first one. Okay? Why is that bond, that blue bond, so likely to break in a radical fashion?
It's a weak bond.
Why is it a weak bond?
It's a single bond.
It's a single bond.
They're both withdrawing electrons.
Both of those oxygens are highly electronegative, withdrawing the electrons away from the bond. Okay? Not only are they highly electronegative, they have the same electronegativity, which means the pair of electrons doesn't really favor one side or the other, it splits evenly. That bond can be cleaved with heat. That's an awful lot of structure stuff to draw. But the critical part of that was the OO bond. Sometimes you'll see reference to ROR, R-O-O-R. It's the OO bond that's generating your radical. What's oxygen? It's ROR without something else out there. It's the same functionality. Okay? Where do we get the bromine radical?
Bromine. You have two.
Put it next to another bromine. This molecule has all sorts of kind of nasty, weird things that can go on with it. Because this reagent, you should remember from first semester, is an electrophilic addition reagent, not a radical addition reagent. This is an electrophile. But given the proper circumstances, like this elemental species and now say enough light energy, light can cause that bond to break homolytically where they each become a radical. Okay? So ROR is a big tip-off. Heat, light. Light is sometimes written as H nu because that's the equation for the energy of light. Right? That's our photon. So that's where these things can come from. When we get down to the carbon radical, you might be like, well, where does that come from? Right? Well, we could try and just copy that out and say, well, it must have just another carbon out there. Problem with that is we have an alkane bond, low electronegativity, not likely to happen. So the carbon radical comes from using one of the other radicals, okay, forcing it to form. Okay? Reactions. Your textbook goes into a lot more detail behind each of these radical mechanisms. I'm kind of saying it's just first semester. I will build a quick kind of review video of radicals so that you can break down the pieces behind their individual mechanisms. Their mechanisms are different than our standard mechanisms because we're moving one electron at a time as opposed to two. Okay, so the terms that you should remember or vaguely recall from first semester would be propagation. Elongation is kind of propagation. I actually started with the wrong one. The I. So propagation's our middle one. What's the I one? Initiation. We have to make the radical. Propagation, our reaction has to continue. And then termination. Kill the radical. Okay? Those three steps, you have to be able to look at a reaction and be like, this is how those things would come out. Okay? When we look at our reaction summaries, these are pretty much all, all. I think these are all the radical reactions that you will be expected to know from chapter 25. And within that context, I would also kind of argue that that's what you're expected to know. What did I just do?
Got rid of the chlorine part.
I got rid of the chlorine one. Why did I get rid of the chlorine one?
It makes too many products.
Look at how many products we get with the chlorine one. All of those products form. That's a giant mess. When I run a reaction, okay, do I want a whole bunch of different things to happen or one thing to happen? One thing. Chlorine is not synthetically useful. Okay, so the textbook will go through and explain why chlorine and bromine are different. You might be able to address that right now. What is the difference between bromine and chlorine? Size. Which means the chlorine radical is less stable. Which means what's it going to do? React as fast as humanly possible. Which means you get a bunch of different products. Because the bromine radical is more stable, it will spend the time to isolate and make one particular product. Okay? So that's our alkanes. When we move to alkenes, you can see Br2. Notice this one's a little bit weird here. This is not a radical mechanism. That reaction is actually a standard electrophilic addition reaction. Why is it listed on here? Br2 acts as an electrophile. What is an alkene? Well, I can do an addition reaction. So Br2 can be very dodgy to deal with. Okay? But if I see Br2 and say, thought it was on there, but it's not, light, I'm now saying I want to do a radical reaction. In that radical reaction, I end up doing a substitution. Just like up here. Br2 and light can give me substitution. Br2 and darkness or nothing gives me an electrophilic addition. So I have to be very careful with that reagent. Okay? Which is often why chemists don't use Br2 in the presence of alkenes to do a radical reaction. Because we could get a different reaction happening. What do we use instead? NBS. What is NBS? Very small concentrations of Br2. Those small concentrations of Br2 facilitate the radical reaction. Okay? Last one, HBr. HBr we saw as a standard electrophilic addition. Okay? Notice we're also adding ROR. ROR is radical. Radicals do the opposite of what you want them to do. So if we just added HBr to the pi bond, where would the bromine go? The bromine would end up going to the less substituted position. Sorry, more substituted position. Where does it end up with radicals? The less substituted. Radicals do the opposite of what you would expect. Okay? If you're like, well, how do we know it goes to the more substituted position? That's looking at the charge breakdown, end of the last lecture. Okay? So, addition reactions with radicals. We'll break this down really quickly. We use light to split ROR into rho. Thank you. Okay? That light or heat reaction is now your initiation. Those radicals will now react with the most accessible thing. The most accessible thing in this case is going to be hydrogen from HBr. Why from HBr and not from the alkene?
Because it doesn't have one like you, it's not.
The alkenes absolutely still have hydrogens.
Bond's easier to break.
Why is the bond easier to break?
Difference in electronegativity.
Large difference of electronegativity. Okay. The other part of it is concentration, which clearly you can see that concentration is listed up there. So like two people laugh, the rest of you are like, what the hell is he talking about? There's no concentration. Concentration's never listed in a reaction. It's assumed for radicals. Sucks. Deal with it. Radical, radical, radical. The end result of those, we get an alcohol. That's pretty useless. What else do we get?
Bromine.
We get the bromine radical. The bromine radical will now react with the most reactive thing, or the available thing. What's the most reactive available thing?
Alkene.
Hydrogen from HBr. What's it produce? HBr and bromine radical. The net result is nothing happened, but that's the most likely step. So that will continue to happen until it sees the pi bond. Now it can react with the alkene. Radical, radical. We're now going to form a bond between one of those carbons and the bromine. Should I put the bromine here? Or should I put the bromine here?
The blue one.
Why the blue one?
Because the radical is going to form on the
Okay. So there's two answers to this. It's the less substituted one, which ultimately means I memorize the radical reaction and I know the radical reaction places it at the least substituted position. That works. Okay? That's not following the chemistry. That's following the end result, the answer. If you know the answer is obvious. Which sounds kind of stupid, but that's how most of OChem is taught. Okay? If we follow the chemistry, one electron from the pi bond came out. What happened to the other electron of the pi bond?
Radical.
It's a radical. So when we do our bromine reaction, we either place the radical here and the bromine there, or we place the bromine here and the radical there. Which of those two is more likely?
The blue.
The blue. Why is the blue radical more stable than the red radical?
Because it's formal charge of, it's got a no formal charge on the, it's not
It can
full
hold
octet,
it.
but that gives you a formal charge of 4 on your carbon, which,
Radicals most closely approximate carbocations. Okay? Because of that, I want to place the radical where I would have the most stable carbocation. Where's the most stable carbocation? Tertiary position. The blue one is favored. That radical now floats around and encounters
HBr.
HBr. And we end with our final product. Why does it not say do this? Does everybody see what I drew? Okay, draw the product. I see a lot of people going, yeah, I totally saw what you did. So you were listening to me because you nodded your head. And then I said, draw the product. And you did nothing.
And you get a
Draw the product. Doesn't have to be right. Draw the product of the red arrows. Do the blue arrows confuse you because they're overlapping? Is that a yes or a no?
The BR goes in there.
The bromine would go in there. Why can't that happen?
Ketones.
Because you get a radical on a hydrogen.
What's the other half?
Oh.
I'd form a hydrogen radical. Are hydrogen radicals stable? No. That's why it cleaves in the blue fashion, not in the red fashion. Okay? Each of those kind of stability arguments is what you have to use to be able to build forward to get to your answers. That is challenging, or you memorize it. And I fully accept you're going to have to memorize some things and not others.
Is it also partially a electronegativity difference? The bromine's going to be less willing to donate that into a bond?
Maybe.
Would it be more of a
I would argue it's not going to really matter. Yeah. Okay. So we could break it all down nice and neatly there. Okay, what happens in this case? Notice it's an alkene, right? Same thing. What's different? What did I do?
You only give it roar.
Only gave it roar. So what does roar react with? The alkene. So what would our product be? Everybody see that? We kind of took it and turned it.
Well, then-
Agreed or not?
No.
As a single step.
Oh, yes.
Is that structure stable?
No.
No. What does it need? It needs to react with something to neutralize the radical. What's the most reactive thing in solution? You could be like the other radical of the roar. Concentration. The roar concentration is next to nothing.
Itself.
What does this other radical react with? More alkene. When I run this reaction, how many alkenes are being reacted?
Avogadro's number.
Many. Probably not Avogadro's number unless you're a chemical engineer. Okay? Because if we look at 1, 2, 3, 4 carbons, 48 plus some hydrogens, you're looking at 50 grams worth. We don't run reactions at that scale. Okay? Chemical engineers are going to go a lot higher than that. Okay? But we aren't running reactions at that scale. Okay? But even then, we're cutting it down by what? A half? So instead of being Avogadro's number, 6.022 times 10 to the 23rd alkenes, I'm using 3.01 times 10 to the 23rd alkenes. That's still a lot of alkenes. Okay? The amount is never specified in OCHEM, or rarely specified. The times that it is specified is because we're giving you a hint. Watch out for this. You need to use 2 of these. In this case, you don't need to use 2. How many should you use? All of them. Well, you're like, well, how many did I put in there? We have to create a notation that would allow us to show that. There's our radical. That reacts. We get a new bond. New radical. Now what happens?
It continues reacting.
Reacts again. New bond. New bond. Everybody get it? Okay. What we're forming is what is known as a polymer. Okay? Polymer chemistry is tricky to deal with. It also sucks to have to draw out 1,000,000 of those things. And 1,000,000 isn't even close to what we're aiming for. So when it comes to polymers, we come up with a shorthand notation. What happens if I copy and paste what's within the black parentheses? If I copy and paste here, did I repeat it?
Yes.
Yeah, how about if I copy and paste it that way? Also repeats. So what I could do is draw parentheses around it, and for this reaction, I could say my answer was N. What is N?
The number of
The same number of times you didn't tell me how much I had. Right? Make sense? Polymers are neat because if you change that number, you change the properties of the polymer. If it's 2, it's probably a liquid and not very useful. If it's 1,000, it's now a nice long chain. Okay? It might actually start to hold some structure, and maybe we get a material like plastic. Okay? So changing that number makes a big deal. Okay? What we just addressed there is what's known as a radical polymerization. Polymerization because made a polymer. Radical because we used radical. Okay? So, there's kind of a nice little stepwise, having it polymerize the other direction. So, what might you expect from this one?
Conjugated pi bonds. Are those 2 different reactions?
It's up to you. Did that flash really weirdly for anybody else?
Yes.
Okay, just checking. I was on the receiving end of that one. The pi bond is what created the backbone, right? We had this backbone, and then it alternated like this all the way across, right? So if we go through and look, there's a pi bond and a pi bond. So it's now just a question of reacting those 2 pi bonds with each other. What's the added wrinkle with this? There's another pi bond, which could mean that could also polymerize.
But does it matter?
So we could get, it's not that it doesn't matter, we could get a polymer chain going that way with a polymer chain going that way, a polymer chain going that way. This one could come that way. This one could even connect up. We end up with what is known as a cross-linked polymer because there were multiple places within an individual monomer that it could polymerize. Does that change the properties? That prevents kind of rotations because it's now locked into place. Okay? So we get a cross-linking of that polymer. Okay? Ultimately, that's not really what I care about because what I care about is the next part of this. Wait, what did I do?
You took away the word.
Rohr's gone. Well, what does an alkene do when I react with an alkene? We might just say, well, nothing, because alkenes don't react with alkenes. They aren't active enough to force a reaction. Okay? This is why Nobel Prizes come about. We look at a reaction and say, that shouldn't happen. But I'm going to mix it anyway, just for, giggles, or accident. And what they ended up noticing they got out of this was this. Like, what the hell? How did that happen? So you go through and you look at the pieces and try and align the pieces. Okay? And what we've got is known as the Diels-Alder reaction. But does that alignment look right?
No.
What had to happen? I had to rotate about that bond to get that alignment. That alignment now allows the reaction to run. In the previous orientation, the reaction never ran. It's only when it aligns here. Well, what's the difference between this orientation and that one?
Higher energy confirmation.
It is a higher energy conformation. Why?
Because you've got
Cis and trans.
Cis and trans? When do we use cis and trans? Shh. With pi bonds. Did the pi bond change from cis or trans?
Yeah.
None of those pi bonds are cis or trans.
Well, not the pi bond, but the structure.
The structure. What's the structure where it's cis or trans? What is it cis or trans about? I'll give you a hint. We'll color code it. Bright red. What is it cis or trans about? A sigma bond. Sigma begins with, like the letter, S. This is an S-cis. Why do we call it S-cis? Because it's a cis orientation about the sigma bond. That's the referencing behind S-cis or S-trans. To get a Diels-Alder reaction to work, you have to be S-cis. It does not happen S-trans. Okay? Reaction runs through, we get the Diels-Alder. We could go through and study this. A lot of people saw this in the lab, so we'll go kind of real quickly through the next review slide behind it. It's a cyclic alkene addition. Okay? We're reacting alkenes with alkenes. We can go through and evaluate what things were broken, what things were formed. And as we discussed in the lab, we could really break this down. Broken, what did we break? Try again. 3 pi bonds. What did we make? 2 sigma. And we made 1 pi bond. That is 6 different things happening in this reaction. If we look at a substitution reaction, there's 2 different things and we got 2 different mechanisms. If we get 6 different things happening, how many different mechanisms could there be to explain it? A lot. Okay? This is where being very kind of choice or careful about what you're looking at can help you with your predictions. Did I break this pi bond or this pi bond? Are they broken in that new drawing?
Yes.
Yes. Are they broken? No. What did I draw? A resonance structure. Because it is a resonance structure, they are one and the same structure. All I've done is shifted my perspective on it to help me change my view on the pi bond to recognize the pi bond never actually broke. It just changed its referencing. Which means I can get rid of the 3 pi bonds. I can also get rid of the 1 pi bond. When we look at the Diels-Alder reaction, there's only 2 things that happen. I form 2 sigma bonds. If we think about a mechanism, and now comes down to the order in which those 3 things happen. We can either do it all at once, or we can do it stepwise, which sounds very familiar because that sounds an awful lot like substitution. But we're now looking at it from an addition perspective. So both of those are potential options. How would we know which one was correct?
Test it with something that can rotate.
You have to test it. So when we think about mechanisms, and you're like, oh, I had to memorize this mechanism in this reaction, how did someone just sit down, stare at it, and be like 20 steps of a mechanism? How'd they do that? They didn't. Okay? They mixed a bunch of stuff together. They got started with one thing, they ended with one thing and said, how the hell could that happen? This is one way it could happen. Then they go back through and they find to design an experiment where they can prove each of those intermediate stages happened. What you guys unfortunately have to do is now either memorize what somebody else did or apply the chemistry to be able to balance your way through it. Okay? Kind of makes sense? As far as Diels-Alder goes, there is an answer Diels-Alder play posit video. I think it's called Diels-Alder Explanations. Watch that. Once I'm convinced everybody has watched that, we'll talk about and actually look at reactions. Okay? This is just the setup for it. I want you to have some baseline conversation or baseline knowledge before we actually look at example problems. Make sense? Okay. Nomenclature, everybody's favorite. If you have not had me, this should be memorized. Okay? And you might think, God, that's a lot. That is nothing in comparison to the amount of stuff that you should have memorized for nomenclature. But if you can memorize everything on that slide, you've probably answered 80 to 90% of the questions you'll see on an exam. Okay? You can reason your way through it. You will not be tested for, did you use the proper spacing, dashes, commas. You'll be expected to get, of 4 answer choices, which one is correct. If you know these rules, you can do that. Okay? There's plenty of people that think you should be able to do the full name. That's awesome for them. They can push that content. I think it's a complete and utter waste of time. Okay? If I don't know how to name a compound, its feelings aren't hurt. Okay? If I know that I'm going to die when I touch it, that's kind of more important to me. Okay? My feelings are hurt. I want to know how it reacts. That's where I'm going to spend my time. Okay? So, next part, first semester. Okay? We have this rule called the Kahn-Ingold Prelog rules. If you haven't heard that name, don't worry about it. I learned it when I started teaching here. Okay? Alkenes, we have E and Z, or trans and cis. Okay? Trans and cis are not a nomenclature system. You have to refer to them as E and Z. That does not mean trans and cis won't show up and you aren't responsible for knowing them. You just have to realize they're not a nomenclature system. Okay? So if you're on the test and it says, which of these is the IUPAC name, and you see trans, wrong. It is not IUPAC. Okay? Chiral, R and S. You may also see plus, minus, lowercase d, lowercase l, capital D, capital L. The meaning of all of those systems are different. Don't cross streams. The biggest one you need to deal with is R and S. Okay? For the others, that's kind of first semester or biochemistry. You can talk to me about details. Then you got the rules. You need to know the rules. Okay? The biggest part with dealing with R and S nomenclature is right here. Which way is my hand turning?
Give me a second.
Yeah, don't worry.
Anti-clockwise.
What? You were just trying to break me. Which way is my hand turning? Did it actually change the direction of my hand? No. So your perspective on the molecule can change the assignment. That's why we have the rules. You have to look at the molecule from the proper angle. You look at it from a wrong angle, you get the wrong assignment. Okay? All sorts of shortcuts first semester. If you are consistently right with your shortcuts, continue to use them. The issue I've had with every single shortcut is I'm not consistently right. I have to redraw molecules to get the proper orientation. Have to. Okay? Like I said, you got a shortcut that works, fantastic. Go for it. You can even tell me about it. I will probably find a way to screw it up and have to go back to this. Okay? Which does bring up kind of an interesting point. A lot of people will be like, oh, I totally have this shortcut. It totally works. And I go, yes, it does totally work. With the exact same success rate of me flipping a quarter. It's either R or S. It's either heads or tails. Typically where students find that their new process that solved it all and made it so much easier was a coin toss, and they didn't discover that it was a coin toss until they took the exam, and it started landing tails. Okay? So be very careful with new processes. As long as you've tested them enough and you trust it, that's okay. You can try and run them by me. I have a hard time with them. Okay? But you can try and run them by me, and I can see if I can break them. Okay? So, advanced naming practice. Here you go. Take a swing. I'll give you... There's really 3 of them. If we look at the ACS, you should be able to solve every ACS question about a minute and a half. So I'll give you 5 minutes for three names. Weakness. One option behind this is we could go through with that very first one and identify those high priority functional groups. Let's actually identify them where they are. So there's one, there's one, there's one. When I go through to find my longest carbon chain, it must contain my highest priority functional groups. Okay? My recommendation is that you go through and you circle the longest carbon chain that contains them. Okay? Most commonly, students will circle this, because when you circle there, how many carbons do you get? 8. And if you circle the blue, you get 7. You go, oh, 8's more than 7, so it must be 8. It has to contain the highest priority functional groups. Okay? So we've got 7, so we're looking at a hept. Okay? If you go back and review my nomenclature videos, okay, hept is our core chain. We then need to specify the hybridization of that backbone. In that backbone, we have some sp2s with the alkene. So that hybridization then needs to be heptene, okay, for the alkene. I have to say where it showed up. Okay? To know where it showed up, I have to be able to number my carbons in the backbone. So I either go left to upish or upish, downish left, right? Okay, to figure that out. The aldehyde is the highest priority functional group. How do I know that?
Memorization.
It is. Okay, if you go back 2 slides, it lists the aldehyde as the highest priority. Or not highest priority, but higher priority than an alcohol. 2, 3, 4, 5, 6, 7. Okay, so the alkene started at position 4. So this is hept, 4-ene, that says 4. Okay, and now I want to specify the highest priority functional group. That's what ends my whole name. The aldehyde is the ending of this. To end a name of a structure with an aldehyde, it's Al. Okay? We should specify the location of the highest priority functional group. In this case, it's going to be position 1. Where are aldehydes going to be found?
Position 1.
Position 1 or position end. Okay? They can only be found at the ends of your chains because that's where aldehydes exist. Okay? So because of that, that 1 is very often dropped from the name. Not always. It's supposed to be there. IUPAC says it's supposed to be there. Most people just flip a bird to IUPAC and just ignore it. Okay? How do we deal with the rest of it? Okay, well, I've accounted for the aldehyde. I've got the backbone. I've got the alkene in there, but I haven't identified the substituents. The alcohol is a substituent because it's lower in priority than the aldehyde. And then I also have this carbon chain. How do I name an alcohol if it's lower in priority? Hydroxy. Okay. How do I name a 3-carbon chain? Propyl. We throw in the Y end to reference it as a substituent. Okay. Where was the propyl found? Position 3. Where was the hydroxy found? Position 7.
7 hydroxy.
Putting the name together, I now have to organize the substituents. How do I organize them? Alphabetically. Hydroxy H comes before P propyl, and I get 7-hydroxy 3-propyl hept 4-ene 1-al. And I'm still wrong.
How come?
You haven't specified.
It's E or C.
The alkene has cis or trans, E or Z configuration. You need to specify that in the name. If we go through and look at that alkene and break down the rules for it, it is going to be the trans configuration. How do we specify trans? E. Where did the pi bond first show up? 4. 4E, 7-hydroxy, 3-propyl, hept 4-ene 1-al. Now you're right.
Don't you also have
We do have chirality within this molecule. Is it specified?
Oh, no.
No, so you can't name it. Make sense? You're like, exciting. That was 5 minutes to solve one of those that you told me to solve all of them in 5.
What's the shorthand for ketones?
Oxo. If it's in the chain, if it's the highest priority, it's own at the ending. So you get suffix or prefix. Okay, so let's double back on that. That's one of the reasons why I like this slide. So the question that he just asked was ketones. How do you name them? If they're the highest priority, where do they go? Highest priority functional group, instead of ending with ane, ein, ene, that last E, that E becomes own. So you end the entire name with that. What if the ketone isn't the highest priority functional group?
Oxo.
Now it gets the oxo. Okay, and it moves further out or moves into a substituent on the chain.
All right, give us a hard one again.
What do you mean again? There's a bunch of them up there already.
Oh, it's kind of easy.
We move to the next one. It's a little bit easier because we didn't have to deal with that branching. We got 1, 2, 3, 4, 5, 6. So we've got hex. Okay. They're all carbon-carbon single bonds, so hexane. Okay. What is our highest priority functional group?
The aldehyde,
We have an aldehyde
hexanol,
or a ketone.
hex.
You all correctly said aldehyde, so hexane, officially 1-al. Okay. Whereas the ketone, yeah, that gave away the numbering. The aldehyde was the highest priority, so it gets the lowest number. 1, 2, 3, 4, 5, 6. 4 oxo, hexane, 1-al. Cool.
Let's get a hard one.
I hate freaking nomenclature, so don't push me on that. Okay.
This one we understand how to get it.
For the next one, hex, you'll notice I'm starting right in the middle of the name. What I'm looking for is that root structure. So hex. Actually, let's switch that up. So hex, that would be 6 carbons.
No, there's no cycle.
This is one of the biggest, most common mistakes. I saw a lot of people looking at me like I was an idiot. That's good. Don't make that same mistake. Okay? For it to be in a ring, we have to see the word cyclo. We don't have the cyclo, don't start adding it. 6 carbons in a line. 1, 2, 3, 4, 5, 6. Okay? 2, ene. Position 2, sorry. We typically read left to right. Reflex, I go the opposite direction. Okay, why might I do that? People that have had me know that answer. People that haven't may not. When are you going to be tested on nomenclature? Stupid way to phrase that. You're going to be tested on a test. How are you going to be tested on nomenclature? Multiple choice. Okay? What are the odds if we ask for the name that we're going to give you the name as the structure is read left to right? Not very likely. Because what are most people going to do when they try to answer that question? Read it left to right. Okay? So why are you getting that question right? Did you know nomenclature? Or did you just know enough that when you read left to right, you got the answer? Okay? So it is very common on multiple choice exams to see the numbering switch. Instead of reading left to right, you read right to left. Or you read like the first one did. What happened up here? Top to left. Okay? So don't just assume left to right. If you're going to go from a name to a structure, it ultimately doesn't matter, except now you have to match your structure to the exam. The exam's probably going to do the exact same thing with these. So if you start immediately going right to left, maybe you can whittle away some answers by numbering there. So at position 2, I have an alkene, like that, right?
No.
That would be going from 1 to 2. Okay, the alkene name has to show up from where it first appears. 2 to 3, oic acid. It's a carboxylic acid that needs to show up where? At position 1. So position 1 was over here. No. Okay, this is why it can be helpful to go through and number. We said this was position 2, which made this one 1, 3, 4, 5, 6. Position 1, I need the carboxylic acid. Oxo. Oxo meant our carbonyl, our ketone. That's at position 4. There's my oxo.
It could be an aldehyde also.
Could it be an aldehyde?
The chart?
The oxo name could be an aldehyde, but it would require what?
So
That the
aldehydes can only be
carbonyl is being placed at the end of the chain. Because it's in the middle of the chain, it by definition is not an aldehyde, it's a ketone. At the 6th position, we have the hydroxy. Make sense? Okay. Know how to name the pieces. If you look at all the work that I went through and did, we highlighted a bunch of pieces, and you'll notice I didn't even rewrite the whole name. Okay? This largely comes from being, well, I'm going to be tested on as a multiple choice exam. I don't need to rewrite the whole name. I just need to be able to organize those pieces. Make sense?
There's no E and Z.
Since no E or Z was specified in the name, I don't have to worry about how I draw it, which means I'm going to draw it the easiest way. Trans is a lot easier because it gives me that more kind of flat shape.
They could give it to you though as like a twisted one.
They could potentially twist it and make it a C. C.
Curly.
It's kind of a C, but I meant cis.
Yeah.
Double bond, but not specify it here. That's still fair game. Okay? Hooray, nomenclature. Okay? Ultimately, it's just practice and memorization. You have to know some old dead white guy's rule. Okay? Some names are actually still getting worked out. Okay, so nomenclature as a system is still constantly getting revamped, and we start adding to the rules. Okay, so electrophilic addition with electrophiles. This gets a little bit weird. Okay, this is ultimately review. Okay, so if you've already memorized all your reagents, you can shut down and not worry about it. Okay, if you have a hard time memorizing those reagents, what I went through and did is when I looked at all the electrophilic addition reactions, I tried to classify them according to certain patterns that I saw. One of those patterns was that if the leaving group was stable, I ended up with some kind of three-membered transition state or intermediate. If the leaving group was unstable, I got a four-membered transition state or intermediate. Why is that important? If I get a three-membered transition state, okay, and one of those bonds is going to break. Should one of those bonds break, first off? Yeah, why?
Ring string.
Ring string. Okay, so something's going to have to come in and cause those bonds to break. Okay? That something coming in is likely going to bring in electrons. Where is that something going to attack this three-membered ring?
On the opposite side.
From the opposite side of the structure. Which means when we look at the end result, those two things are now on opposite sides of the old pi bond. That would be known as an anti-addition. Okay? What if I had a four-membered? Okay? Well, now when we go through and do it and we break open the ring, where are those two pieces? They're on the same side. We get a syn addition. So if I know something about the intermediates of the mechanism, I can predict the orientation of the pieces that got attached. Okay? It is very thin and loosely based in certain mechanism aspects. But this patterning, at least for me, helps me to group and see those stereochemical alignments. If you don't like that, that's fine. You have the textbook that doesn't talk about those patterns in that way, and you just memorize the crap out of those mechanisms. Okay? The problem is that you have a hard time then connecting different reactions to each other, and each thing becomes its own unit of information to memorize. Okay? The more individual pieces you have to memorize, the harder it becomes. Okay? So, if we go through and look at the first one, leaving group is super stable. The pi bond comes out, attacks the Lewis acid, the leaving group leaves. One of the other conditionals of this one is that Lewis acid must have a nucleophile, or must have electrons to act as a nucleophile. Okay? So that if I go through and look at something like this, isn't bromide a great leaving group? Do I get a three-membered transition state with the addition to HBr? No, why not? The pi bond comes out, attacks, leaving group leaves. There's the second conditional here. The Lewis acid, the thing that just accepted electrons, must also be a nucleophile. To be a nucleophile, what must it have? Electrons. That hydrogen does not have electrons, which means it cannot loop back we end up with a carbocation. We don't fit that mechanism pattern. Okay? We then form our three-membered transition that says, trust me, it says transition. It does. Or intermediate. Does our reaction continue? Well, what is the atom La? Is it okay as a positive? Okay? If it is, then it stops. It's stable. Okay? Does it have to be positive? It depends how it started back here. Okay? If it is unstable, the nucleophile attacks backside, and I get an opposite alignment. Notice we don't see an opposite alignment here. Why? Or how do we know?
Well, it's a sigma bond, so you can have rotation on the bond.
We have a sigma bond that can do free rotation, so it may not look like it was added on the opposite side. That is a sneaky trick the ACS does. Okay? And how else, or what else should we be looking for? Wedges and dashes to specify the orientation in space. Because it's not specified, we can't reference it that way. Okay? If the leaving group is unstable, what happens? Okay? Well, the alkene attacks the Lewis acid, but now the leaving group is unstable. It cannot exist on its own. So instead of leaving the structure, it immediately attacks back. Why can it attack back? If these electrons come out to the Lewis acid, what happened to that carbon? Becomes positively charged. That's why the electrons can swing back in. They get added on the same side. Okay? You see a variety of question marks showing up in there. A lot of that depends on what those individual species are. Okay? We don't have a whole lot of time here, but I do officially have like 30 seconds. Okay? This is a list of pretty much all of the reagents you're required to know for our electrophilic additions. What you should be able to do is to classify them. This is a 3-member. This is a 4-member. Okay? Or a 4+ member. Some of this becomes tricky because we're not looking at a Lewis structure. We're looking at a formula. If I draw out Br2, okay, what would my leaving group be? Br minus. Is that a good leaving group?
Yes.
Yes. That's a 3-member. HBX. Okay. Whoops. Part of this is knowing the reactivity here. What's the reactivity of that structure? Where's the electrophile? Where's the Lewis acid? Almost everybody jumps on hydrogen because hydrogen's always positive. No, it's not. Hydrogen becomes negative when it's bonded to something that is less electronegative than it. Hydrogen's 2.1. Guess what boron is? 2.0. Hydrogen's actually negative in this case. The boron has an empty p orbital. The alkene dumps the electrons into the boron, which means hydrogen's the leaving group. Is that a good leaving group? No, that's horrible. Guess what? That's a 4-membered. Okay? MCPBA, the P standing for phosphorus. No. Peroxy. MCPBA is the abbreviation from the name. For those of you being like, I didn't know that. I know, it sucks. Sometimes we do that. Remember THF? DMSO? Okay, you're responsible for knowing those. You're responsible for knowing that that Lewis structure, oh God, is a big one. That's a chlorine. Where's the P? That's your peroxy. Okay, what happens? Does that look like a good leaving group?
Yes.
Why?
Because it's big and there's a lot of resonance.
Resonance. Good leaving group? 3-membered. Okay? You should be able to go through and attempt looking at each of these. Again, you'll probably have to dig into actual Lewis structures to look at them. Some of them are very tenuous connections at best. OSO4, permanganate, both of those are very weak connection back to this pattern recognition, but I would argue it's there. Okay? It doesn't guarantee your patterns. What it does is help to organize your thought to make it easier to process. Okay? With that, we got to be done. I will be going to the tutoring center or